Hello everyone. Today we are going to discuss regarding hyperconjugation. We have completed two of the electronic displacement. This will be your third of the electronic displacement, the hyperconjugation. So this is also really very much important. You will find one or two questions which is directly based on hyperconjugation, where your plus I effect won't work it out, but their hyperconjugation will have some examples, right? So what is hyperconjugation? It's a special kind of resonance, or we can say that this we can also say that it is no bond resonance. Okay, means in this type of resonance there is no involvement of bond. Okay, so you will see that bond is not available, but still the resonance is taking place. Okay, so for this type of reaction, we say that this type of resonance, we say that it is delocalization of sigma electron. Until now, you have heard about that delocalization of pi electron. Here we'll see delocalization of sigma electron. Okay, sigma bonded electron, correct? Sigma bonded electron. Okay, where it is in between carbon and hydrogen. Okay, carbon and hydrogen will have sigma bonded. So in it, this movement will take place. So where it will take place, suppose carbon and hydrogen bond is there. So this bond, where it will shifted, this can be shifted towards the three different possible or probable orbital. That will be your first will be your, it will shift towards empty p orbital. Okay, second probable will be your partially filled p orbital, and third probable shifting will be from sigma electron, that is CH bond. The delocalization will take place towards the pi anti-bonding orbital. Correct. These three type of shifting you will be seen over here in the hyperconjugation. Okay, so if empty p orbital means we are talking about carbocation, because if it is carbocation, suppose this is a carbocation, this will be shape for carbocation, and for carbocation this orbital will be empty, right? If it is carbocation, this orbital will be empty, and this is p orbital. Okay, so we are talking about this for empty p orbital, we are talking about this, and then wherever the alpha carbon will be there, that hydrogen will be shifting over here, that we are going to discuss just right now after this introduction part. And then partially filled p orbital, how it will work, it will be like something radical, carbon radical. So this also we can explain it like, see, this is your sigma bonded for your free radical, and that radical will be present over here in this p orbital. Okay, so this one, your radical is available in this p orbital, so we call it partially filled orbital. Okay, which orbital? So p orbital. Then how pi star orbital will work? Suppose you have double bond. Okay, double bond, I will not write like this because we have to show how the shifting is taking place. So here the carbon, two bond will be available over here, and the third one will be okay, this one we need sp3. So what will happen here, the bond will be there with the hydrogen. Okay, we have to draw like this. This is sp3 s. Okay, this is sp3, this is s. Here also sp3s, sp3s, hydrogen, hydrogen. Okay, now to this one alkene will be there here, sp2s, sp2s, and the pi bond will be like this. Okay, unhybridized p orbital, one electron will be available over here, one electron will be available here. It will be like lateral overlapping. Here also it will be lateral overlapping. So this is a pi bond, right? So wherever this pi bond will be there, one pi anti-bonding is also available, right? One pi anti-bonding, and this will be like opposite to this pi. Now what is happening? This electron will shift towards your pi anti-bonding, and this entire bond will shift over to your pi, in carbon as a negative charge. Okay, so this explanation we will see here how it is working over here. But before that, we will see just condition how the hyperconjugation is taking place. So it is like the hyperconjugation, like wherever the uncertainty or unsaturation will be available, wherever the unsaturation is there, near to that or next to that, sp3 carbon should be available. sp3 carbon, okay, it should be available. Or we can say that alpha carbon should have sp3 hybridization, correct? We can write like this. We can say the next carbon of the unsaturation should be sp3, or we can say that alpha carbon should have, and we should have the sp3 hybridization. Okay, alpha carbon should be sp3 hybridization, correct? And in that alpha carbon, okay, in that alpha carbon, minimum, I'm telling about minimum, maximum 3 hydrogen can be possible, but minimum 1 hydrogen should be present. Okay, minimum 1 hydrogen should be present. So this hyperconjugation takes place. So first we'll take this example like MTP orbital, how it is working. So we'll see the MTP orbital, how this type of hybridization is taking place. So this is carbon. Okay, here hydrogen, hydrogen, hydrogen. The unsaturation, this is MTP orbital, means in this carbon's p orbital it is empty. Okay, so now what is happening? This is your carbocation. Okay, now how this carbocation is getting stabilized, that only hyperconjugation. What will happen? This bond will be shifting over here. Okay, so what will be the next structure? This will be like double bond carbon, and see now this plus charge is getting neutralized with the double bond, and here it will be H plus, and see in between there is no bond, so that's why we call it no bond resonance, and this will be resonating or contributing or hyperconjugating structure 1. Then secondly, what will happen to neutralize this unsaturation? What will happen? This bond will shift over here, and the new bond will form like this: carbon, here one hydrogen, here it will be H plus, and here hydrogen, and then double bond carbon, hydrogen and hydrogen, correct? And this we call it second hyperconjugating structure. See, in the resonance also we'll come to know that the more number of resonating structure or contributing structure or canonical structure, the structure will be that much stable, correct? So now there is two hyperconjugating structure. What is the meaning of this hyperconjugating structure? It means you can say that this positive charge is stable with the three contributing structure. It means suppose we are taking, like, suppose for one contributing structure it is taking 1 second, so for three contributing structure, it will take 3 seconds. If someone is having six hyperconjugating structure, it means it will take 6 seconds. Some compound is having 9 hyperconjugating structure, means it is stable till 9 seconds. So that way we are just observing the stability of like carbocation, right? On the basis of hyperconjugation. So this is the second. Now what will happen to neutralize this positive? What we will do? We will shift this bond over here, and then the next canonical, or we can say hyperconjugating structure, will be like this: H plus, and then here the double bond and carbon and hydrogen, correct? Now what will happen? See, this positive charge was over here in this carbon, so what will happen? Again it will form over here only. So the next structure will be your, it will come over here, and that next structure will be your, it will directly go and it will form like this, right? So the positive charge again it is forming. So this is, you see, three hyperconjugating structure. So if it is primary, so this carbocation is primary, right? Because only one carbon is attached. So this is primary carbocation. Likewise, if secondary carbocation is there, suppose this one, and then carbon, here positive charge, here hydrogen, and here hydrogen, hydrogen and hydrogen. This is secondary. What will happen? This side three hyperconjugating structure it will form, and this side three hyperconjugation it will form. So how many hyperconjugation total? 6 hyperconjugating structure. But in primary how many? Only 3 hyperconjugating structure. Likewise for tertiary what will happen? See, hydrogen, hydrogen, hydrogen. Here it will be carbon, positive charge, and then here hydrogen, hydrogen, and this place also, because tertiary we are drawing the tertiary three CH3 group will be available. So in this, I'll use different color, so it will be visible for you, clearly visible for you. So these three will form three hyperconjugating structure. These three will form three hyperconjugating structure, and this three will draw three hyperconjugating structure. So there will be in total 9 hyperconjugating structure. Got it? There will be 9 hyperconjugating structure. So you just tell me which carbocation will be more stable, or we can say which carbocation will be less available to react. Okay, either you can say the stable, or you can say less available for the reaction. Okay, so that means only see here for 3 times it won't be available. For in this case 6 times it won't be available that carbocation. Here the 9 times it won't be available this carbocation. So the stability will be like your tertiary will be more stable than secondary, and secondary will be more stable than primary. So on the basis of hyperconjugation we are designing this, right? So tertiary will be more stable than secondary, and secondary will be more stable than primary. And this is a type of which type of hyperconjugation we are dealing over here. So if we will write, sorry, if we will write type of hyperconjugation, which type of hyperconjugation we are dealing over here? It is empty p orbital. Okay, see, day by day the questions pattern and in the competitive examination, the asking pattern, like how they are really involving towards too much basics. So you should know the basics. Like if you know that there are 9 hyperconjugating structure, or 6 hyperconjugating structure, or 3 hyperconjugating structure, it won't really work. So what you have to do, you have to just find it out now. The more basic is, they'll ask you the type of hybridization it has involved. So it is a empty p orbital, because see where this hydrogen bond is, like this bond is shifting, that is in the empty p orbital, right? So this we call a type of hybridization is empty p orbital. Likewise, partially filled p orbital, that will be the second types. And what is there here? The free radical will involved. Okay, so free radical, we'll see how the free radical involvement is there in the hyperconjugation. So suppose here the alpha carbon, wherever you are seeing this hyperconjugation, there should be an alpha carbon where the hydrogen will be like in that hydrogen should be available. Minimum one hydrogen should be available, then only this hyperconjugation part will taking place. So here one radical will be there. So hydrogen and hydrogen. So in simple way, what is happening? First step, it will be, we know that there will be 2 electron in this bond. Okay, one it will be mutually shareable in between carbon and hydrogen. One electron is from carbon and another electron is from hydrogen. So what will happen? This I'll use different color. So that color will let you know how this movement is happening. So one electron will move towards hydrogen, and another electron will move towards this carbon, this bond, and this electron will also move towards this bond, and it will form carbon carbon double bond. See, one electron, and from this side one electron, so it will be double bond. And now the radical got vanished, and it has formed a new bond. So what is happening here? One hydrogen, and this hydrogen will be as an radical, correct? This hydrogen will be as a radical. So now this will be your first hyperconjugating structure. And then in the second, to neutralize this unsaturation in a bond, or we can say that no bond, this bond will move towards here, and then your next contributing structure or hyperconjugating structure will be like this. This radical will be available over here, and then double bond carbon, here hydrogen, this place is also hydrogen. So this will be your second hyperconjugating structure, and the third one will be, this bond will shift over here and it will just neutralize. Okay, it will form this bond, and then this hydrogen will have radical, double bond carbon, here hydrogen, here is one hydrogen. This will be your hyperconjugating structure 3. Now if you are just suppose now, and again you can do what you can do it, you just I'll use different colors so it will be easy for you. See here what will happen, this radical will give one electron over here to form a bond, and now this bond is having 2 electron, one is from this carbon, another is from this carbon. So what will happen, this electron will move towards here, to form a bond between carbon and hydrogen, and another electron will move simply towards this carbon as before, right? So what will be the final structure over here? This will be your final structure. So there will be three. So it means we were having three alpha hydrogen. So three alpha hydrogen means here three hyperconjugating structure, right? You just see one, two, three. So if we have secondary again, I'm drawing like carbocation. Okay, see here radical, here hydrogen, it will be secondary, hydrogen, hydrogen and hydrogen. This is secondary. So see three hyperconjugation, this side also three hyperconjugation, and we are talking about only alpha carbon or alpha hydrogen. Okay, this is not alpha. Okay, alpha means the next carbon. In that carbon, how many hydrogens are there? Not in the same carbon where the unsaturation is there. Okay, this won't take participate. It won't be participated, correct? The alpha hydrogen is only participating, not the same carbon where the unsaturation is there, correct? So 3 and 3 total, how many hyperconjugating structures? 6 hyperconjugating structure. Okay, likewise for tertiary, see hydrogen, hydrogen and hydrogen. This is radical, here hydrogen, hydrogen and hydrogen. In this place hydrogen, hydrogen and hydrogen. So see here 3, 3 and 3, 3, 3 and 3. So total, this is tertiary. So total 9 hyperconjugating structure. So the stability order, how it will work over here, the radical. So stability will be your 3 degree will be more stable than 2 degree, then 1 degree. So again I am telling you the stability, what I have told you regarding the stability. Stability is like the unavailability of radical, okay, to react. Unavailability of a radical towards the reaction. So in the primary, the unavailability like 3 times only, okay, because this one is rotating to the 3 hyperconjugating structure. For secondary, 6 times it is unavailable. For tertiary, 9 times it is not available, right? So 9 times means it is quite stable. So that's why 3 degree, 2 degree and 1 degree. And then the second type of question they may ask, types of hyperconjugation. Okay, so types of hyperconjugation, this is partially filled p orbital. Okay, it means it is moving, the hyperconjugation is taking place towards the partially filled p orbital, correct? And one more thing, this arrow is fish hook arrow, okay, because it signifies that one electron is shifting, and this arrow is your double headed arrow, which means entire both the electron is shifting, correct? So that you have to make yourself that much knowledge you should have, that fish hook arrow and double headed arrow, what is the meaning of that, okay? And this single sided arrow means this is reactant to product, and this double headed arrow means it is a resonating structure. It can be from this side to this side, or this 1 to 2 or 2 to 1, it can be shifted, right? So now this third type of hyperconjugation we were discussing about your unsaturation or pi bond, okay, or we can say alkene. Okay, and alkene, how this thing is happening? So your again the alpha carbon should be available, and that in that alpha carbon there should be minimum one hydrogen, then only this will be taking place. This is your carbon, single bonded carbon, hydrogen, here one hydrogen, and what will happen? Your lateral overlapping, we will show it over here. So here 1, 2, 3, one hydrogen will be there, which will be making bond. So I'll just change a color. So here one electron, here one electron. What is happening? This is lateral overlapping. Okay. So now these two electron will shift towards your anti-bonding. Okay, these are the anti-bonding pi orbital. Anti-bonding pi orbital, which we are symbolizing like this is anti-bonding. From where it came? See, in MO, you know that sigma bond, pi bond, non-bonding, then pi star, which is anti-bonding, then sigma star, which is anti-bonding, right? So these two are bonding molecular orbital. This is non-bonding, okay, non-bonding molecular orbital. This is your pi anti-bonding, and this is your sigma anti-bonding. or we can say ABMO, anti-bonding molecular orbital, these two. So this is from MO, molecular orbital theory, okay, or molecular orbital diagram, whatever you say. So this you should know, that you will come to know in chemical bonding unit. Okay, you have completed your chemical bonding, you are very much sure about this, what I am talking about, this anti-bonding pi orbital. So what will happen? These two, both the electron will shift towards this pi anti-bonding, correct? Once it is shifting, then what will happen? This bond will break, and this bond will break, and this entire, both the electron will shift towards this carbon in this orbital. The next structure will be your carbon, and then here hydrogen, it will be positive, as it is like hyperconjugation we previously we have discussed. And then carbon, here it will be your okay, in this carbon it will be like hydrogen, okay, and here it will be double bond, and then here in this singly bonded, and you can say here two hydrogen is there, we'll just draw it, and one negative charge over here, right? And then contributing structure, you can say this is the first, and second will be to neutralize this, it will move over here. So here hydrogen plus, here singly bonded, double bond carbon, here singly bonded, then negative charge, and this hydrogen. Then what will happen? This will be canonical structure 2. I'll draw this side. So third will be like, it will move over here, and then here it will be hydrogen, hydrogen, here double bond carbon, here carbon H plus, and then hydrogen negative, hydrogen, and here hydrogen. So there are, this is third hyperconjugating structure, correct? 1 2 3. Now at last what will happen? This will be shifting over here, and this will be shifting over here, and then finally you are getting this structure again, correct? So likewise we are showing that hyperconjugating. Okay, so here also it will be like that's why in this type, in this third type, the question will be like, which double bond will be more stable, right? One will be like this one, A, second will be your B, and third will be your C. That you were making, Sedgwick product and your Hofmann product. So we know that more substituted double bond is more stable, right? That we are telling, right? What we call the more substituted double bond will be more stable according to Serge product, right? So it means C will be more stable than B, B will be more stable than A. But the same thing is happening over here also. You see here, if one alpha, like if one single bond, then like one alpha carbon, there three hydrogen is there, so it will be three hyperconjugating structure. See here, here three hydrogen will be there, here also three, because this is carbon, no? In this carbon, three hydrogen is there. In this carbon, three hydrogen is there. So six hyperconjugating structure, or we can say six alpha hydrogen. You have to just count how many alpha hydrogen is there. And based on that, you can say that this many hyperconjugation is taking place, and this compound is that much stable. Okay, so six hyperconjugating structure, six hyperconjugating structure, or six alpha hydrogen. In B, how many alpha hydrogens are there? See, 1 2 3, 1 2 3, 1 2 3. So total 9 alpha hydrogen. In this case, 1 2 3, 1 2 3, 1 2 3, 1 2 3. So total 12 alpha hydrogen. So see again, with this way also, based on hyperconjugation also, we are solving the same thing. C will be more stable than B, B will be more stable than A. And according to Serge product also, more substituted double bond will be the more stable product, right? So this like that you have to solve, whether through hyperconjugation you are solving or Serge product. So you have to solve like this. And next question they may ask, type of, okay, type of hyperconjugation. What type of hyperconjugation is involving in this unsaturation double bond? So here your answer will be pi antibonding orbital is taking part in these hyperconjugating structures. Okay, understood? So couple of example I'll give you. You just solve those example. So that will be like all the three type of hyperconjugation together. I'll give you the examples. You just solve it. It will be based on how many alpha hydrogen are there. So that many hyperconjugating structure can be possible. Okay, so you can say just count the alpha hydrogen. Okay, so first will be your suppose. Okay, okay, then B, just you have to count alpha hydrogen. Okay, just you have to count alpha hydrogen, nothing else. This is radical. Okay, this is radical, and then here we can give and one more. This four only you count and just write your answer in a comment like in A how many alpha hydrogen is there. The whatever the number of alpha hydrogen, that many type of that many hyperconjugation structure will be there. So just be careful about to counting the hyperconjugation. Here what I'll do, I'll just put plus charge over here in this carbon. This positive is there. Okay, and then I think here the positive charge is not required. You just count here. And just talking about alpha hydrogen. Now one is radical, double bond, and one carbocation I'll give. One carbocation I'll give. That's it. So this carbocation is in this carbon. Okay, so out of like in this A B C D, you have to just find it out. You have to just find it out how many hyperconjugating structure is there. Correct. So comment it that your answer. So for today, this much only.